Welcome to my Show Me about converting repeating decimals to fractions. This skill is usually part of an algebra lesson where part or all of the objective is that the students will understand that repeating decimals are rational numbers. Rational numbers are numbers that can be expressed as ratios of integers. If we can convert a number to a ratio of integers, then it is a rational number. This skill also demonstrates the important idea that we can subtract one equation from another. Let's convert 0.4 repeating to a fraction. First, skip a line on your paper. On the second line, write x equals 0.444 ... How many digits are actually repeating? 1. Take 10 and raise it to the first power for 1. 10 to the first power is 10. We're going to multiply the equation on this second line by 10 and put that result on the first line. So go back to the first line and write 10x equals 4.444 ... If you're wondering where that fourth 4 came from, remember that those dots represent an infinite string of 4s. I have as many 4s as I need, and more. Now, subtract the second equation from the first equation, or subtract the equation on the second line from the equation on the first line. 10x minus x is 9x. 4.444 forever minus 0.444 forever is 4. Now divide each side by 9, and x is 4/9. To verify that this is right, take 4 and divide it by 9. Nine doesn't go into 4. 9 goes into 40 4 times. 4 times 9 is 36. 40 minus 36 is 4. And we're right back where we started, which means we're going to keep getting the same thing over and over and over again. So we do have the right answer. This decimal is equal to 4/9. Let's try another. This time, let's convert 1.23, with the 2, 3 repeats forever, into a fraction. Again, skip a line on your paper, and on the second line, write x equals 1.232323 ... Notice that every time I do this, I rewrite the repetend, the repeating set of digits, 3 times. That's just a habit of mine, but I think it works well to remind you of all the numbers that you have to work with. This time, 2 digits are repeating. 10 to the second power is 100. We're going to multiply both sides of this equation by 100 and put the result on the first line. So we have 100x equals 123.232323 forever. As before, take the second line, the equation on the second line, and subtract it from the equation on the first line. 100x minus x is 99x. And 123.23 forever minus 1.23 forever is 122. Divide both sides by 99. X equals 122 divided by 99. To verify the answer, take 122 and divide it by 99. 99 goes into 122 one time. 1 times 99 is 99. 122 minus 99 is 23. We're going to have to work with decimals here, bring down a 0. 99 goes into 230 twice. 2 times 99 is 198. 230 minus 198 is 32. Bring down another 0. 99 goes into 320 3 times. 3 times 99 is 297. 320 minus 297 is 23, which puts us right back where we were the first time we wrote out a 2. So the next digit's going to be 2, and then 3, and then 2, and then 3, and so on forever. So we do have the right fraction. This fraction is equal to 1.23 repeating forever. Let's wrap this up with a slightly more difficult example. This time we're going to have a decimal number that doesn't start repeating until its second digit. As before, skip the first line and write x equals 3.2848484 ... Two digits are repeating. 10 to the second power is 100. We're going to multiply each side of this equation by 100 and put the result in the first line. 100 times x on the left side, and 328.4848484 forever is 100 times 3.2848484 forever. As before, subtract the equation on the second line from the equation on the first line. 100x minus x is 99x. All of the infinite series of 84s cancels to this point. The tenth place still intact. 328.4 minus 3.2 is 325.2. I'm not terribly keen on having fractions inside my fractions, and decimals are fractions. Let's eliminate the decimal at this point so that we don't have to deal with it later. Multiply both sides of the equation by 10. So we have 990x equals 3,252. Divide both sides by 990. We have x equals 3,252 over 990. Notice that the digits of each, the numerator and denominator, add up to multiples of 3. 3 plus 2 is 5, plus 5 is 10, plus 2 is 12. And in the denominator, 9 plus 9 is 18. Since their digits add up to multiples of 3, these numbers are multiples of 3. If you look carefully, you'll also notice that both numbers are even. That means that they're also multiples of 6. So, let's divide each by 6 to reduce the fraction. When we do that, we get 542 in the numerator and 165 in the denominator. To verify that answer, we should divide 542 by 165. 165 goes into 542 3 times. 3 times 165 is 495. 542 minus 495 is 47. We want to need decimals. Bring down a 0. 165 goes into 470 twice. 2 times 165 is 330. And 470 minus 330 is 140. Bring down another 0. 165 goes into 1400 8 times. 8 times 165 is 1,320. 1400 minus 1320 is 80. Bring down another 0. 165 goes into 800 4 times. 4 times 165 is 660. 800 minus 660 is 140, putting us right back where we were before we added that last 0, just 2 iterations ago. That means the next digit's going to be 8, and then 4, and then 8, and then 4 forever. In other words, we do have the right fraction. I hope this has illuminated a relatively arcane skill. It is a fact that there are calculators that will do this for you. There are all kinds of shortcuts to it in certain situations. And it's not a terribly common skill out in the real world. It is important, however, to understand that this is something you would have to do to prove, in a certain from a decimal form in any way, to prove that a decimal number is rational. If you can't do this with a decimal number, then the decimal number is irrational. And that is important when it happens, and it does happen sometimes.